Alright guys, let's talk real briefly tonight about state functions and about a funky little term called enthalpy. So a state function, this is one of these concepts that seems really hard to get sometimes, but essentially what a state function is that we're going to take a property that only depends on its present state, or really I guess we could sort of say it only depends on its initial and final conditions. What this means is if I'm going from point A to point B, all that matters is that I started at A and that I ended at B. That it doesn't matter if I had to make a whole bunch of steps in between it. So, like, I mean, what would that be? Well, let's say that something wasn't a state function. If something wasn't a state function, then I would start here at step A, go to A1, to A2, to A3, to A4, to A5, and then finally I would get to B. And for some properties of matter, it doesn't really matter that I had to take all these steps. All that matters is that I started here and ended here. And then for others, it matters a lot that I had to go all of these different steps. And so a couple of good examples would be something like work. Work, it matters a lot how you get there. It's what we call a pathway dependent thing. So like if I said, hey, I want you to take something from my room up to the main building, but before you go there, I want you to go stop by the amphitheater and by the sun sphere and then go up to the main building, then your work is going to be a lot different than if I just said, hey, take this box and carry it up to the main building straight in one line. So work and heat work that way, but what doesn't work that way is energy. And what we're going to work towards today in this lesson is something called enthalpy, which is related to heat, but is also a state function. So it only depends on its proper, on its initial and final conditions. So this is basically what I just said, summation of it. So heat and work are not state functions. They are pathway dependent. We're going to see that there are a lot of different things that are pathway dependent, but we're honing in here on thermochemistry. Energy is a state function. So it doesn't matter how we got there really. What matters is what was the initial condition, what's the final condition, and we can just makes our calculation so simple. The math works out a lot easier if something is a state function because you just have to worry about initial and final conditions. You don't have to do every single step in the way. You can just go that straight line through the whole thing. So let's do a real quick calculation then for energy. Remember that this is our energy equation that we talked about in the last video. And so our change in energy is equal to the heat plus the work. And remember that the signs of these things matter. If something is flowing into the system, then it's positive. If work is being done on the system, then it's positive. If heat is flowing out, it's negative. If work is being done by the system, then that's a negative. And so, I mean, this comes out to be a real simple calculation. We've got our delta E, and it's going to be equal to, we've got 15.6 kilojoules of heat. It's an endothermic process, and so that means it's going to be a positive heat. So 15.6 kilojoules, and we're going to add that to 1.4 kilojoules. And why is that a positive? Because it says work is done on the system, so that means work is going into the system. And they're both in kilojoules, so I'm not going to write the units as I work the problem. I'm just going to write them here at the end. We add those two things together, and we get 17.0 kilojoules of energy. Piece of cake. About the simplest equation that you'll ever have to see in AP chemistry. The only hard part, of course, is just making sure that you get the signs right. And I got to tell you, they love to throw out some simple questions like this on multiple choice part of the test because they are pretty simple. You can do the math pretty quick, but it tells them, do you know what endothermic means? Do you know what work done on and by the system means? So let's talk real quick about that. In chemistry, if there's work being done, typically it's a gas that's related. And so there's a situation where either a gas is being compressed or the gas is expanding and therefore doing work on the system. So those are our two scenarios here. So in the case of compression, the volume is going to decrease. That means work is going into the system. So if we look at that last example, that would essentially be what's going on. Work is done on the system. Okay, so it's being compressed. And in expansion, the system is doing work. It's pressing out and moving things away from itself, and therefore work is going out of the system. So that leaves us with a nice easy little equation here that work is equal to the negative of the pressure times the change in volume. Remember that the change in volume, any change in is final minus initial, and so we can punch those out pretty quickly. So let's look at a somewhat more complicated example, really not that hard, but we'll read through it real quick. Balloon's inflated to its full extent. We're heating the air inside of it. In the final stages, the volume of the balloon is going to change from 4.0 to 4.5 times 10 to the 6 liters by the addition of a certain amount of heat. So we're adding heat into the system, so that means heat is going to be positive. And so I'll just make myself a quick little notation to that effect to make sure that I know that. So I'm just going to say positive here. Okay? And in the case of my work, really, you're going to do final minus initial, all that, but how is the work going to be? Well, in this case, I know that the system, since the balloon is expanding, I know that the system is doing work on the balloon, so the work is flowing out of the system, and so that means in this case that work is going to be negative. I'm just going to make a note of that as I do the math here. Okay, so let's go ahead and punch out this math real quick. Remember that our overall equation, okay, delta E is equal to Q plus the work. But also remember that what really is going on is that work is equal to negative P times the change in volume. And so I'm going to go ahead and work this part real quick, and then we'll go back and plug that in. So this part actually works out pretty simply though as well, because the pressure is 1. Okay, so that means I've got a pressure of 1 atmosphere, and then my volume, I've got 4.5. Okay, and I'm just going to do our little e to the 6th, and then minus 4.0 e6. Sorry, that's a decimal. Guys know I can't draw decimals when I do this. We're going to do that math real quick. That's going to give us really some funky units, and I didn't actually write the units, but I'll write them here. And so that's going to give us an answer of 5.0, and I'll write it out this time, times 10 to the 5th liters times atmospheres. Now, liters times atmospheres doesn't make a whole lot of sense to us, and that is conveniently enough we have been given a conversion factor there. So I'm going to convert that real quick, and I'm not going to actually show the whole conversion factor because I trust that you guys can do that. But if I convert that to joules, I'm going to get 7.9. Whoops, that is not correct. If we're jumping ahead in the problem, I'm going to convert that to joules real quick, just by quick conversion. Essentially, I'm multiplying it by 101.3. And so that is going to give me, oh, you can't write without a pen, Arnold. And so that's going to give me a joules work value of 5.07 times 10 to the 7th. 10 to the 7th joules. Okay, so I'm going to go then take this and plug it in here. But remember what we said earlier, it's negative. I kind of know that anyway because I got a negative sign over here. But I'm going to plug that in as a negative. I'm going to plug my heat in as a positive. And then I'm just going to add them together. And I mean, so that comes out pretty easily. So I'm going to just sort of rewrite this over here where I've got a little bit more room. Delta E, that's an awesome delta E, or TPE as the case may be. So my heat is 1.3 times 10 to the 8th joules. And then I'm subtracting my work. Remember, again, I'm subtracting the work because the system is doing work, and so therefore the work is flowing out of the system. Again, guys, sorry for my writing. It's been a while since I've had to write a whole lot on the pen tablet here, and as you can see, I am slightly out of practice. Not that I was ever all that good in the first place. So that gives us a final value of 7.93 times 10 to the 7th joules. You could convert that to kilojoules, or you could get real excited and convert it to megajoules or whatever. You can just leave it as joules unless it asks for the answer in kilojoules. And so that is going to be our correct answer. And again, the math a little bit more complicated than the previous problem. And obviously, we had to calculate the work because there was an expansion of a gas. But really, I mean, the math isn't that difficult. What is hard is remembering your sign conventions. And that's what tends to be the killer on these particular types of problems. So we like to do the math. If you're in AP Chemistry, you're probably pretty good at math, and we like those problems. But we would much prefer to do things heat-wise if we had a good old state function. So enthalpy is the way that we're going to get around the fact that heat is not a state function by essentially turning it into a state function. So here's what enthalpy is. Enthalpy is H, and it's equal to the energy plus the P times V, okay? In other words, plus the pressure times the volume, so the expansion again. And so what we're going to do is I'm going to just real quick sort of show you how this leads to heat and how we relate this. You're not going to have to do this or prove this or anything like that. And I know sometimes you hate it when there are derivations. So if there are, just hit fast forward on the video. That's all good. And since we can't actually measure enthalpy itself, and just like we can't really measure energy itself, we can measure the change in. I'm going to take all of these things and essentially make them the change in, except pressure, because we're typically working under constant pressure scenarios, right? So I'm going to change everything to that. So delta H is equal to delta E plus the P times delta V. Okay, so nothing terribly complicated there. What I'm going to do in my next step is I'm going to substitute in the equation that I already know for delta E. So that's going to give us delta H is equal to Q. Hey, I drew a Q correctly. I'm pretty proud of myself there. You guys should be too. And then, hold on, let me just take that little plus sign away real quick there because, oh, I did not mean to take all of that away. That is awesome. Hold on, let me write that again. So Q, hey, I still drew it, minus P delta V. And if you're wondering why that happened, because remember, that's what the energy equation itself is. And I'll pop back there in just a second so you can see that. Okay, so this is the energy equation that we used, right? Q plus work, and work is actually negative P delta V. Okay, and what you can obviously see here right away is that these two terms are essentially going to cancel each other out. Okay, negative and a positive. And this is all assuming that the pressure is constant. If the pressure is a constant, then there's deltas there, and that's going to sort of mess things up a little bit. But for our scenario, we're going to assume that they are constant, and so what that's going to leave me with then is that the change in enthalpy is equal to the heat at a constant pressure. And that is going to be pretty awesome because that's going to allow us to do some easier calculations. We're going to do a lot of calculations with enthalpy coming up. Hess's law and standard enthalpies of formation and all that stuff, and that's really sort of the heart of thermochemistry, and it's all due to the fact that enthalpy is essentially the heat at constant pressure. Obviously, it's more complicated than that if some of those terms don't cancel out, but for most of our scenarios, we're generally working at constant pressure, right? I mean, atmospheric pressure isn't usually going to change all that drastically in the lab, assuming we're not like vacuum pumping the air out or something. So this is going to work for us for just about any equation that we're going to need, certainly at our level of chemistry. So enthalpy is a state function, not pathway dependent. That means that for us, only the initial and final conditions matter. And so we can basically say this, that the change in enthalpy is going to be equal to the products minus the reactants. Delta, right? Final is products, minus initial is reactants. And so we're going to use those enthalpies there to do some calculations. This obviously is going to have to change a little bit because we just said earlier that you can't really calculate H on its own, that you've got to work in terms of change in enthalpy. So, I mean, what would this look like? Well, essentially what this looks like in a reaction for us is that what we're really going to calculate a lot of times for a given reaction is we're going to calculate something called the heat of reaction, or more appropriately, the enthalpy of reaction. We're going to write that as delta H sub Rxn. Remember, Rxn means reaction. And so if we just took a simple reaction like combusting hydrogen, okay, which is fun, and maybe we'll do some of that in class, then we could calculate the energy that was released by that. We could say that that was the heat of reaction. We see that it's negative 483.6 kilojoules. It's a pretty fair amount for just a couple of moles of hydrogen, because a couple of moles of hydrogen is like 4 grams, right? So that's not really a lot, and that's a pretty big amount of energy. Remember that it's negative here because it's exothermic. It's going to give off heat as you would sort of expect from a combustion reaction. And so that's going to be our heat of reaction. We're going to do a lot more calculations and stuff with enthalpy, but we're going to save that. We're going to wait till we get to Hess's law here in another couple of videos. For now, just be able to do the simple energy equations, know what enthalpy is, know that you can find an enthalpy of a given reaction, and know that enthalpy is a state function, and of course, what's important, what is a state function? All right, thanks, guys.